Hi, it's Sir Rob. Today I am going to discuss non-linear programming with the theme Foundations and Computational Mastery of Non-Linear Programming, an expert guide to theory, modeling, and Excel solver implementation. Optimization, in the context of mathematical programming, involves calculating the extrema, maxima, minima, or stationary points of an objective function across a defined set of unknown real variables, conditional on satisfying a system of equalities and inequalities known as constraints. Nonlinear programming, or in short, NLP, represents the subfield of mathematical optimization dedicated to solving problems where either the objective function is not linear or at least one of the constraints is not a linear equality or inequality. As always, in the practice of financial management, we should remember to be professional, perform effectively and efficiently, follow standards, and document our work adequately and properly. Our topics for this discussion are 1. The nature and structure of nonlinear programming, NLP. 2. Practical applications of NLP. 3. Solving NLP problems using Excel solver. And lastly, 4. Local and global Optima. And off to our first topic. 1. The nature and structure of nonlinear programming, NLP. This section includes a discussion of 1. Defining optimization and the core distinction from LP. 2. Standard mathematical formulation of NLP components. And 3. Specialized classes of nonlinear programs. Defining optimization and the core distinction from LP. Optimization, in the context of mathematical programming, involves calculating the extrema, maxima, minima, or stationary points of an objective function across a defined set of unknown real variables, conditional on satisfying a system of equalities and inequalities known as constraints. Nonlinear programming, NLP, represents the subfield of mathematical optimization dedicated to solving problems where either the objective function is not linear or at least one of the constraints is not a linear equality or inequality. In Chapter 3, we said that a problem or function is linear if all the following conditions are met. 1. Each term is either a constant or a constant multiplied by a decision variable. 2. Variables are not multiplied by each other. 3. Variables are not raised to powers other than 1. Conversely, therefore, if any one of the three conditions is violated, then the problem or function becomes nonlinear. This structural difference marks the fundamental divergence from linear programming, LP. LP assumes all relationships are straight lines, offering a single straightforward optimal point. NLP embraces curves, reflecting the complexity and diminishing returns of the real world, where the best solution might lie on a peak or in a valley. Furthermore, NLP typically addresses continuous optimization problems characterized by an infinite and continuous set of possible decision variables leading to significantly increased computational complexity compared to LP. A point of necessary clarification exists regarding terminology. While this field is formally known as nonlinear programming, NLP, the acronym is also frequently used to denote natural language processing. This lecture focuses exclusively on nonlinear programming within the domain of mathematical optimization and operations research. Standard mathematical formulation of NLP components. The general nonlinear programming problem can be formally stated in maximization form, although an equivalent minimization form always exists. The core components define the decision variables, the objective function, and the constraints that delineate the feasible region. The general formulation seeks to maximize a function as shown on the slide, subject to constraints, also shown on the slide, where multiple instances of x represent the vector of real decision variables. The objective function is the formula being maximized or minimized. The moment it contains nonlinear terms, the problem is classified as NLP. Decision variables are the quantities you control to achieve the objective. These are the unknowns you need to solve for. Similarly, the constraints define the limits of the feasible region. If any function is nonlinear, The problem is also classified as NLP, regardless of the linearity of the objective function. The constraint system can include inequalities and equalities. Specialized classes of nonlinear programs. Certain subclasses of NLP problems possess specialized mathematical structure, enabling the use of more efficient and reliable solution methods. Understanding these classifications is crucial for selecting the appropriate computational engine. 1. Convex optimization. This highly desirable class exists when the feasible region defined by the constraints is convex, and the objective function is either concave for a maximization problem or convex for a minimization problem. Convex programs share many of the attractive computational properties of linear programs, specifically concerning the reliability of the resulting solution. 2. Quadratic programming, QP. A specific scenario where the objective function is quadratic, containing terms such as x1 raised to the second power or x1 multiplied by x2, but all constraints remain strictly linear. QP techniques are well developed and generally simpler to solve than arbitrary general NLP problems. 3. Fractional programming. This involves objective functions structured as a ratio of two functions, such as maximizing fx divided by hx, where f is concave and h is convex. Such problems, provided the constraints are convex, can often be transformed into an equivalent convex optimization problem. 4. Pre-processing simplification via direct substitution. For problems containing only one or two linear or nonlinear equality constraints, it is often superior to solve explicitly for one variable and substitute the result into the objective function and all other constraint equations.
2. Practical application of nonlinear programming. This section includes a discussion of 1. Financial optimization, nonlinear portfolio selection, and risk management. 2. Nonlinear facility location problems. 3. Engineering design and parameter optimization. And 4. Nonlinear cost functions in supply chain and economics. Nonlinear programming is indispensable across numerous domains where complex physical, economic, or logistical relationships cannot be adequately captured by linear approximations. Financial optimization, nonlinear portfolio selection, and risk management. Financial modeling relies heavily on NLP, particularly in areas involving risk and variance. The seminal work on modern portfolio theory, MPT, by Markowitz intrinsically defines a nonlinear problem. The primary nonlinearity arises because the objective of minimizing portfolio risk variance is a quadratic function of the weights of the assets and the covariance matrix between them. This classifies portfolio optimization as a quadratic programming QP problem, a highly important subclass of NLP. Applications include 1. Optimizing asset allocation for large institutional funds, such as pension funds and endowments, to maximize returns while managing complex risk and liquidity constraints. 2. Advanced risk management models in banking and insurance, where nonlinear models are used to calculate risk metrics like value at risk. Designing robust algorithmic trading strategies, where returns are modeled using complex nonlinear functions of market data. Nonlinear facility location problems. The optimal placement of facilities such as warehouses, emergency stations, or manufacturing plants is a cornerstone of operations research, frequently necessitating NLP models. When optimizing facility location, the objective is often to minimize the total transportation cost, which is proportional to the distance traveled. If the facility location is allowed to vary continuously on a plane, and actual travel distance is approximated by the Euclidean distance, nonlinearity is immediately introduced. The distance formula contains squared terms and a square root, rendering the problem nonlinear. The facility location problem seeks to minimize the sum of the weighted rectilinear or Euclidean distances from the new facility location to all existing demand points. NLP models are particularly crucial when accounting for real-world geographical complexities, such as the presence of physical barriers, for example, rivers or arc-shaped barriers. These barriers introduce complex, nonlinear constraints into the feasible region that must be modeled to accurately reflect transportation costs. often resulting in a mixed integer nonlinear programming (MINLP) formulation. Engineering design and parameter optimization. In engineering and experimental sciences, nonlinear programming is used to optimize the design parameters of physical systems, maximizing performance or minimizing material costs and energy consumption. Many foundational mechanistic models in engineering and life sciences are inherently nonlinear. For example, chemical process optimization often involves complex nonlinear models related to reaction kinetics or thermodynamics. Pharmacological dose-response models, such as those used to determine half-maximal effective concentration or median lethal doses, rely on nonlinear curve-fitting techniques. When fitting experimental data to a theoretical model, the analyst minimizes the sum of squared errors between the nonlinear models, predictions which depend on variable parameters and the observed data, a quintessential nonlinear least squares optimization problem.
Nonlinear cost functions in supply chain and economics. In economics and supply chain management, NLP is utilized for complex resource allocation and cost minimization tasks. Specifically, when the costs associated with production, inventory, holding, or transportation exhibit nonlinear relationships, such as economies or diseconomies of scale, or variable pricing structures, linear models become inadequate. Nonlinear cost functions, which might include exponents or multiplicative relationships to model diminishing returns or penalty costs, necessitate the use of NLP to find the true optimal operating point. 3. Solving NLP problems using Excel Solver. This section includes a discussion of 1. Establishing the NLP model structure in Excel Solver. 2. Formulating nonlinear relationships in Excel. 3. Activating and selecting the GRG nonlinear solving method, and for interpreting solver results messages. Microsoft Excel, through its built-in solver add-in, provides a powerful and accessible platform for modeling and solving continuous nonlinear optimization problems. This add-in is a powerful tool for NLP. Setting it up correctly is key to finding a valid solution. The process involves defining your variables, objective, and constraints directly in the spreadsheet. Establishing the NLP model structure in Excel Solver. Before setting up the problem, the analyst must ensure the solver add-in is activated, typically found under the Data tab in the Analysis group. The spreadsheet model is very much like linear programming problems, except that the formulas of either the objective function or the constraints are nonlinear. The model setup requires mapping the mathematical components of the NLP problem onto the spreadsheet structure. 1. Input cells. These are cells where fixed parameters and constants are entered. You might remember that these are the cells with white or no background colors. 2. Decision variables. Changing variable cells. These are the cells that hold the values of the independent variables which solver is allowed to adjust during the optimization process. These cells must be referenced by the formulas in the objective and constraint cells. Recall that these are the cells with the green background. 3. The objective cell, target cell. This single cell must contain the final formula representing the objective function. In the Solver Parameters dialog box, this cell is specified as the target to be maximized, minimized, or set to a specific value. Recall that this is the cell with the blue background. 4. Constraint formulas. Constraints are established in the Solver Parameters dialog. The left-hand side LHS of each constraint is typically a formula calculated in a worksheet cell, referencing the decision variables, and we usually set the background of these cells to yellow. This LHS cell is then constrained against a right-hand side RHS value, another cell, with a specified relationship, for example, less than or equal to, greater than or equal to, or specialized constraints like integer or binary. Formulating nonlinear relationships in Excel. A spreadsheet optimization model is deemed nonlinear whenever the relationship between the objective cell or any constraint cell and the decision variables is non-additive or non-proportional. Nonlinearity in Excel is introduced through standard mathematical operations, such as multiplication, division, exponentiation, or the use of nonlinear functions, for example, square root, sine, power, log. For instance, optimizing profit where demand is a nonlinear function of price, or where cost includes squared terms related to production volume, immediately results in a nonlinear objective function. The integrity of the spreadsheet model relies on direct functional relationships. Solver requires that the formulas in the objective and constraint cells are directly computed using the values in the changing cells. Complex custom functions, user-defined functions, or UDFs that attempt to modify other cells or workflows involving manual copy-paste operations are incompatible with the iterative, gradient-based nature of the solver algorithm. Activating and selecting the GRG nonlinear solving method. For smooth nonlinear problems, those where the objective and constraint functions are continuous and differentiable, the GRG nonlinear solving method is the default and recommended engine in Excel Solver. The GRG nonlinear method employs the generalized reduced gradient algorithm, which can be conceptually understood as a nonlinear extension of the simplex method used for LP. At each major iteration, the algorithm selects a basis, determines a search direction based on gradients, and performs a line search. This process requires iteratively solving systems of nonlinear equations to maintain feasibility, that is, ensuring the trial solutions stay within the bounds defined by the constraints. Interpreting solver results messages. The solver engine communicates the outcome of the search through specific result messages, which must be correctly interpreted, especially in the context of NLP. 1. Solver found a solution. All constraints and optimality conditions are satisfied. This is the ideal outcome, indicating that the algorithm has successfully converged to a point that satisfies the KKT necessary conditions within the specified tolerance. In convex problems, this is the global optimum. In non-convex problems, this represents the best local optimum found, potentially the global optimum if multistart was effective. 2. Solver has converged to the current solution. All constraints are satisfied. This message suggests that the relative change in the objective function became smaller than the convergence tolerance for the required 5 iterations. If the model is poorly scaled or the solution region is flat, this may indicate that the solver stopped prematurely before the KKT conditions were fully satisfied. Reviewing and tightening the convergence tolerance is often warranted here. 3. Solver cannot improve the current solution. All constraints are satisfied. This condition is rare for the GRG nonlinear method. When it occurs, it usually points toward a problematic model structure, such as degeneracy, potential cycling of the algorithm, or the presence of redundant constraints that should be removed.
4. Local and global optima, finding the true peak. This section includes a discussion of 1. Differentiating local optima from global optima. 2. Necessary and sufficient conditions for optimality, KKT, and 3. Overcoming local optima with Excel Solver. Unlike linear programming, non-linear programming solvers can get stuck on a local optimum, a solution that seems best in its immediate neighborhood but isn't. The overall best, the global optimum? The shape of the problem space determines the difficulty of finding the true global solution. Differentiating between local and global optima. The distinction between local and global optima is central to the difficulty of solving general NLP problems. A locally optimal solution, X*, is a feasible solution whose objective value is the best possible only within an open neighborhood immediately surrounding it. When visualizing the objective function as a landscape, for example, in a maximization problem, a local optimum is akin to standing on a plateau. A globally optimal solution, X***, is a feasible solution that possesses the absolute best objective function value across the entire feasible region. Using the same analogy, the global optimum is the highest peak in the entire mountain range. For general, non-convex NLP, solvers can typically only guarantee that they will return a locally optimal solution. The result is often highly dependent on the initial values supplied for the decision variables, influencing which region of attraction the iterative algorithm converges to. Finding the guaranteed global maximum or minimum is analytically challenging and numerically requires exhaustive search strategies, which are computationally orders of magnitude more expensive than local methods. This difficulty stems directly from the non-convex nature of the problem landscape. Non-linear problems with multiple local optima are difficult to solve. But in many non-linear applications, a single local optimal solution is also the global optimal solution. For such problems, we need to find only a local optimal solution. Necessary and sufficient conditions for optimality, KKT. The Krush-Kuhn-Tucker, KKT, conditions are a set of necessary and sometimes sufficient conditions for a solution to be optimal in an NLP problem, particularly when the problem involves constraints, both equality and inequality. Analytical verification of optimality in differentiable NLP relies heavily on the Krush-Kuhn-Tucker, KKT, conditions. Under general differentiability and constraint qualifications, the KKT conditions provide the necessary criteria that a point must satisfy to be an optimal solution. These conditions relate the gradients of the objective function and the constraints at the optimal point. The numerical search algorithms used in computational optimization, such as the generalized reduced gradient or GRG method, are essentially designed to converge to a point where these KKT conditions are satisfied within a specified numerical tolerance. Specifically, convergence requires the projected gradient of the objective function, the gradient projected toward the feasible region, to be sufficiently small, approaching zero, and the projected Hessian matrix of second derivatives to be positive definite for minimization or negative definite for maximization. The significance of convexity appears once more when applying KKT. In the absence of convexity, satisfying the KKT conditions only guarantees that the solution is a local optimum. However, under convexity, satisfying the KKT conditions is both necessary and sufficient for guaranteeing a global optimum. This relationship confirms why convex optimization is computationally preferred. Overcoming local optima with Excel Solver. Excel Solver provides an option that increases the confidence that a global optimal solution is found. Clicking options on the Solver Parameters dialog box and then selecting the GRG nonlinear tab results in the dialog box. Clicking the User Multi-Start option in the Multi-Start section causes Solver to use multiple starting solutions and report the best solution found from all of the starting points. The population size is the number of starting points used. Solver selects starting points randomly using the random seed, an integer value, such that the points are within the bounds specified. Although providing simple lower and upper bounds is not required unless the require bounds on the variables is selected, the procedure is much more effective when bounds are provided. Checking the require bounds on the variables checkbox and providing bounds before using the multi-start is recommended.
Conclusion and summary. Nonlinear programming is a powerful and necessary tool for modeling real-world optimization challenges that defy the simplifying assumptions of linearity. The mathematical complexity inherent in NLP demands a highly analytical approach to both formulation and computational execution, particularly when utilizing general-purpose solvers like Microsoft Excel's GRG nonlinear method. The reliability of NLP solutions hinges on the problem's underlying mathematical structure, specifically its convexity. For convex problems, including linear and quadratic programming, local optimization is sufficient to guarantee global results. However, for general non-convex NLP, computational output only reliably guarantees a locally optimal solution, making the starting point a critical input parameter that influences the final outcome. Analysts must therefore exercise diligence in formulating non-linear relationships in the spreadsheet model and in setting the Excel Solver parameters, fine-tuning the convergence tolerance, moving below the default 10 to the negative fourth power, or 0.0001, is often required to ensure the algorithm thoroughly satisfies the KKT optimality conditions. Furthermore, for non-convex problems, the use of the multi-start strategy, defined by sufficient population size and strict bounds on variables, becomes essential for extensively searching the solution space and increasing the likelihood of identifying the global optimum. Ultimately, mastering nonlinear optimization requires not only correct mathematical formulation, but also a nuanced understanding of the algorithmic limitations and configuration requirements governing the computational process. There it is. Chapter 5, all about operations research optimization method, nonlinear programming. The references used in the production of this lecture video is shown on the following slides. Thanks for watching and stay safe always.